Well, thank you. It's just really great to be here, and I'm slowly beginning to wake up, so there's hope. And I also want to thank Tom and Christina for all your work in organizing this. And now I know that, so first of all, let me say that I'm going to be presenting a mathematical model, or a couple of them, and you're probably going to grimace at that prospect. And I think all of you are experimentalists, and I'm not aware of any of you who are also theoreticians. So let me just say a couple things about why I'm doing this, because my intention is not to ruin your whole day. I'm sure this is supposed to be helpful. And now, when you approach an equation, this may be you may have heard all this before, but you should look at an equation as though it's a sentence, and the equal sign is a verb. And so when you see an equation, it says something about something is going on, and a sequence of equations amounts to a paragraph, and it expresses an idea. And the kind of model I'll be giving you is called a dynamical model, because on the left-hand side of the equation, it says how something is going to be like tomorrow. And on the right-hand side, it says what's going on today. And so the purpose of the equation is to tell you what's happening tomorrow based on what's happening today. And the variables in the model, you can think of it as like a play. And at the beginning, you set the stage. And the variables are like the characters in your play. And so on the right-hand side, you have the characters that are interacting with one another, like two of the characters may be in love, and a third character may be jealous. And then the left-hand side will say the response of one of the characters to the love and the jealousy on the right-hand side. So then you go to the next day, and you know how everybody is. You plug it back into the same you plug it back into the right-hand side, and you get day 2. So you keep plugging it in over and over again, and that's called iteration. And if you keep doing this, then the plot unfolds. And as you can imagine, the plot may come to a happy ending, which we theoreticians call the equilibrium. Or it may come to not a happy ending. So one of the jealous party might kill everybody else, and then out of guilt kill himself. And that's called an extinction equilibrium. So where it winds up is the equilibrium. And theoreticians really are very interested in that. The other thing is that if somebody knocks on the door and wants to come in, then depending on whether there's space for that person, that's what theoreticians call increase when rare, or invasion when rare. And so those two solution concepts, the invasion when rare or increase when rare, and the equilibrium, are the things you solve for in a dynamical model. And so you'll see that kind of thing turning up here. And then the last thing sort of worth mentioning is, what does it mean to test one of these? Now, you always think that models are tested, right? And you have some idea in your mind that, okay, you plug in numbers for all the, oh, and by the way, the numbers in front of every one of the terms, you can think of as an adjective. So if the couple that's in love has just a small number in front of it, then it means they're not very much in love. And if there's a big number, in front, then it means, or if there's a big number in front of the one that's jealous, you know they're really jealous. So I guess I'm going to have to wrestle with this just for a second here. Yeah. Okay, there we are, hooked up again. Now, so what does it mean to test one of these things? So you might have the idea that you're going to plug numbers in for all the variables and all the coefficients and come out with a prediction okay? And then and then you're going to take some data, and you say, do the data match the prediction? Voila, you've got a tested model. But that doesn't ever happen because no one has the money or time to get all the numbers to make a quantitative prediction like that. You don't have the time to get the data for that. You might not be in the right position to do it. So what happens is kind of a synergy instead. So the purpose of the model is to tell a story. It's like, as I was saying, it's like a play. The plot unfolds from the initial condition, and it unfolds until the equilibrium is reached. And that then constitutes a narrative. And then with your field work or with your experimental work, you take data and you weave it into the narrative. But sometimes you can't weave it in. Sometimes the data fly in the face of what the model is saying. The model says something goes up, and in reality it goes down. Well, then the model gets changed. And so what comes out of this synergy between the empirical discovery and the theoretical storytelling is a synthetic narrative, if you will. And it's jointly owned. It's owned, you all own it, because the theoretical part contributed to the narrative. The data contributes to the narrative. And so that's how it gets tested. It gets weaved in with the data. And that's the objective of it. And so we're not out there trying to, get numbers and, almost in an adversarial way, test the model against the data. No one really wants to do that. Okay, so what about the model? So the issue that I'd like to face or address is what accounts for the integration between the microbiome and the host. And it's been amply documented in the last several, yesterday and the day before, about how deeply integrated the function is of the microbiome with the host. And why? How does that come about? That's the problem that this modeling is addressing. And so let's see. Let's try that. Haha. Now, so from these models, I'll tell you two stories. And then let me start out, though, by getting us on the same page with respect to the definitions. So the definition I like for a microbiome is the one from Josh Lederberg that talks about an ecological community of commensal, symbiotic, and pathogenic microorganisms that share the, quote, body space of a host. And I like the phrase body space, and it's a spatial concept. Now, a holobiont then is a composite organism consisting of a host together with its microbiome, and I do credit Lynn Margulis with that, even though could be some contention on the point. And a hologenome, then, is the union of the host genes with all the genes in the microbiome. And Elena Zilber-Rosenberg and Jean Rosenberg coined that phrase. And the hologenotype is the configuration of the hologenome in a particular holobiont. And then I've introduced that piece of jargon. And so holobiont selection is the differential reproduction and or survival of the holobiont depending on the hologenotype. And now, so here's the first model. But actually, it's the beginning of the first model. The first model comes in two parts. The first part is really elementary. It's, can a microbe coexist with a host? It's a population dynamic problem, not an evolutionary problem. And let's see. So here's the setup for the life history right here. Whoops, let's go back. Let's go forward, and then some button here does this. Yeah, okay. I'm wired for sound, I think. Yeah, I probably got knocked out of shape when.
There you go.
Great. You're my hero. All right. Okay, so here's the setup. So, and in my mind's eye, I always have Carl's in mind because I'm at a Marine station and that's the sort of thing I do. Now this right here is a pool of larval corals, planulae. And here's some algae out in the water. Now, the algae land on the larvae through Poisson sampling. Now, Poisson sampling, so we're on the same page, that's the sort of thing that a Geiger counter has. So when a Geiger counter is near radiation, you hear, right? And if there's a lot of radiation, it's, and this parameter, which you'll see shortly called mu, is the Poisson density function. And so if there's a lot of radiation, you get a lot of hits. And if there's not much radiation, there's not a lot of hits. So what we get here is Poisson sampling from the microbial source pool onto the larvae. And just by the way, Max Delbruck was active showing that there was Poisson's sampling of, in this case, of viruses onto bacteria. And okay. Now the next part is, so some of the larvae get an algae and others don't. This one does, that one doesn't. Now here's the key point, is that the within host population dynamics is that the ones that were colonized grow to a carrying capacity, within host carrying capacity, and those that weren't, of course, don't. Now, regardless of the number of initial colonists, so this larva right here could be colonized by 1, 2, or 3 algae, it doesn't matter. They all come to the same equilibrium at the end. And that's really important because it means the initial colonization condition is erased right here. So then we come along and we get to this point. And at this point, we get the new larvae are being made, and W right here is the fitness of a holobiont that has no algae in it, and W sub 1 is the fitness of a holobiont that has species 1 of algae, because we're only doing one species so far. So, so each of these 2 genotypes can contribute to the larval pool. Now, also, the microbial source pool gets replenished. I'm going to watch my time here. And but here, of course, there are no algae here, so they don't contribute anything. But of those that do have algae, the number that they contribute is K, the number within each, times W1, which is the fitness of the holobiont. So I've termed this the multi-level fitness for the algae because it takes into account both the within host success that the algae has, as well as the between host, as well as the success of the holobiont as a whole that it's embedded in. So, so this is a dynamical model then, and you just go round and around on this and see what happens. Well, the parameters of the model, as I've already laid out, are that K right here is the equilibrium within host, W0 is the holobiont fitness of with no algae or with 1 algae, and D is important. That's the colonization parameter. It's the probability that an algae from the algal pool gets to the surface of a larva. And then the Poisson density function is mu right here, And this is a Poisson distribution, for those of you who are into that. In any case, the bottom line is that the conditions for host microbe coexistence is this. It's dk W1, it's got to be greater than W0. Now, what's dk right here? Now, suppose just for the sake of discussion, that the carrying capacity for microbes is 100. And suppose that the probability that a microbe in the water gets to a larva is 1 over 100, so that the product of this is 1, okay? Because this is usually going to be on order 1. So the condition is that the fitness of the holobiont with larva has to be greater than the fitness of the holobiont without larva. So if that's true, then the algae coexist with the host, and that's the population dynamics of it. And if you rearrange that, it means that it's relevant to say that the carrying capacity of the larva of the algae in the host has to be greater than this whole stuff in order for them to coexist. Okay, the plot thickens. Now, suppose so now it gets into evolution and the notion of the hologenome. So here, if we have two alleles, which are indicated here as gears, and so there can be allele 1 and allele 2, and two types of algae, and that gives rise to 12 possible hologenotypes. And what's interesting here is that there are two inheritance processes going on simultaneously. So for the nuclear part, we're getting random union of gametes right here in the usual Hardy-Weinberg type sense. And for the microbial part, we're getting the independent colonization by Poisson sampling of these two algal types. So they're going on simultaneously, and in parallel. So that's how you construct the hologenotypes initially. Then these have a within-host population dynamics, so that if there are no algae, of course, you don't get anything. If they're colonized by only one algae type, you get its corresponding carrying capacity. And if they're colonized by two algae types, then they come to equilibrium with a within-host population dynamics, such as the Lacca-Volterra competition equations on a within-host basis. So this comes back over here, and then now we get holobiont selection at this stage, repopulating these pools. Now, so let's talk about the case where we're just going to focus on the algae. Now, the idea behind the hologenome is very appealing. It's that the genome, the nuclear genome, can be, so to speak, extended, that we have an extensible genome involved. And you're not stuck with a fixed number of loci that are on your chromosomes, but you can go ahead and add some more genes as needed. And so I found that very appealing. But the question we face is, does it work? So let me show you, let me back up here. So let's take the case where we only have genetic variation that's in the, I'm trying to get this button here, only have genetic variation in the algal pool, and no nuclear genetic variation, because this is the hard part. This is the new part. We all know how this works. And then ask the simple question. Suppose the gene in the two algal cells are neutral, selectively neutral. Suppose they have the same effect. That's where you would start if you're analyzing the model. It's just, what would you expect? You'd expect neutrality, right? If they were both had the same effect on fitness, then the gene frequencies shouldn't change. But let me show you a simulation where we have an array of 100 larvae on the row and 100 larvae on the column. So we have 100 by 100, so a lot of larvae out here to be colonized. And now, yeah.
If you press one more time, it starts.
Okay. So now these are larvae. Every dot right here is a larva colonizing, is an algal cell colonizing a larva. And then gradually all these larvae get, well, almost all of them get filled. So the code right here is that if there's a cell that's black, that means neither algal colonized. If the cell is green, it's that one. If the cell is red, it's the red alga. And if it's yellow, it got colonized by both. So you see it fills up, even though the initial condition was different. In one case, we started with mostly red. In the other case, mostly green. And the summary slide should be coming up in a second. Yeah. So you see on the left-hand side, we started mostly with red, and we came to what looks like the same outcome as starting mostly with green. And then the numerical values of the gene, of the allele frequency, of the strain frequencies are below. So on the right here, we started out with mostly red, and here mostly green. And what you see is that in both cases, they converge to 50-50. So that means that's a problem. That means there's no neutrality. The two alleles, two strains, have the same effect on the holobiont, but nonetheless, their gene frequencies, their strain frequencies converge to 50-50. And that's completely different than the Hardy-Weinberg situation with nuclear genes. And the reason is that if an allele is in abundance to begin with, it doesn't benefit from it, because if that strain colonizes any given larva multiple times, it still realizes the same carrying capacity out of it. Whereas if a larva is colonized by only one instance, it still comes to the same carrying capacity within that host. So the fact that you can't benefit from, and that the initial colonization frequency is erased during the within-host population dynamics, that then limits the ability of any strain that has a numerical advantage to take advantage of its numerical advantage. And that winds up leading to a 50-50 ratio. Now, the implication of that is that directional selection has to fight against this. So now take the case where one of the strains really does improve the fitness of the holobiont. And so you would expect holobiont selection to fix on the strain that conferred the highest fitness. But it can't, because it's fighting against this tendency, this central tendency from the colonization process. And here's a summary of that. Right here. So if the fitnesses are in this order, where the fitness of the holobiont is 1 if there's no algae in it, is also 1 if there's a red algae, is 2 if there are both types of algae, and is 3 if there's the green algae in it. Now that ordering of fitnesses, if that were on nuclear genes, you know right away that it would fix over here on the green one. But whether it does or not depends on the parameter D. If the colonization is low, then it does fix. But if the colonization is high, you wind up getting this polymorphism out of it. So for that reason, there's a real problem in trying to see holobiont selection on the whole as explaining the integration, or any trait, but including the integration of the microbiome with the host. Now you might say, but you could say that's a feature and not a bug, because the other way to look at it is that under directional selection, you still wind up preserving variation. So if the environment changed, you'd still have both strains around. So directional selection on the nucleus, of course, reduces variation and eliminates the unfavored gene. And if the environment changes on you, you're kind of stuck and you have to wait for a new mutation to turn up. But here, you still have the variation. But on the other hand, you don't get the success in achieving adaptation through this process. So I've suggested instead that there's another type of process, which I think some of you have alluded to in your own studies, which is that an alternative hypothesis would be that we have a kind of adaptive assembly going on, which I've named host-orchestrated species sorting, drawing on the terminology in microbiology about, the microbes are everywhere and the environment selects. So here, the idea is that the things are everywhere and the host selects. And so I've set up a little animation here to show you how this would work. So consider three types of microbes. One which contributes a lot of its carrying capacity, so gives up some of its carrying capacity to help the host. And this gives less, and this one gives none. And the within host carrying capacity K is either low in one situation or high in another situation. Meanwhile, there's a system, which I'm assuming is the host antibody response, which is that if the host is colonized by a nasty microbe, then it's repelled, hence the little tanks. And not so much with this one, and if it's colonized by this type of microbe, which gives a lot of its carrying capacity to improve the host survival, then it's not repelled at all. So let's consider, let's run a simulation of how this works. Okay. So one with a small carrying capacity approached the host, but can't get in at all because its K is too low. So this one has a higher K, and it gets in, but it's kicked out. This one comes in and is welcomed, if you will, by the host, but on the other hand is excluded by competition with the one that doesn't give as much. So you're left with an outcome in which the host has a microbe in it that provides some help, not as much help as possible over here, but something. And meanwhile, it produces some antibody response to it, but it's not as much as it would if it were a poorer host. So you have a kind of situation right there, which is an integrated host microbiome situation, or host microbe situation. It's not optimal, but it does exist. And so some process like this would be an alternative story to a holobiont selection on a hologenome story. And so that's what I've been suggesting there. And as a result, we might consider amending the definitions a little bit. And I just last week came across still more articles discussing the assembly So I think a lot of people are coming up with the idea, or have independently come up with the idea that the explanation for the microbiome host integration has to do with the host controlling what gets in. And if that's the case, then we might want to redefine a microbiome right here to be a neighborhood that's still spatial, a neighborhood controlled by a host. And so this would also work for plants and the microbes right around the roots and things like that, as long as the host can control it. And then a holobiont then is a functional unit. We don't have to talk about it as an organism because that gets us into so much trouble and arguments with people. But it's, I think, incontrovertible that it is a functional unit and it's integrated with its microbiome. So this would seem, these definitions would seem to widen the scope of the phrase microbiome in an appropriate way and avoid having semantic arguments about whether the holobiont is a unit of selection or not, because in any case, it's certainly a functional unit. And now, I've also done some work, but I won't go into it here, but I'll just alert you to it, that I've done some work on the evolution of phage in bacteria, and in particular developed a condition for the transition from a lytic phase to a lysogenic phase. And so I'll give you the reference to that, but we won't go into it. But it has some nice predictions, and including how you can get a tripartite holobiont. And I think tripartite holobionts are really interesting. And also, as Thomas mentioned on a day ago, a patient in the hospital is a holobiont, and it's actually a tripartite holobiont if you are interested in phage therapy, because you have the phage, it's going to hit the microbe, and the microbe is living within the host, and it's the host that's suffering from the pathogenicity. So that's about as much time as I have. So the references here that are, in particular, the 2023 one is in the American Naturalist, and then one this year on the Life History Switch. It just came out this year in Virus Evolution. So thank you very much.
Thank you for a wonderful talk. So nice. We have some time for questions, if anyone has any. I can start with one. Oh, okay, there's one over there.
Hi. Very nice talk. I was curious about transmission. So you have sort of sampling in your model, but maybe in different animal systems, there's more fidelity with transmission, perhaps. I mean, that's another subject. So where do you see that in some of your models and I guess conclusions about hologenomic evolution?
Well, actually, the first paper I did right here on that list was specifically about the vertical versus horizontal transmission and doing a holobiont, going back to that holobiont model, life history model, and assuming that there was vertical transmission instead of Poisson sampling. But the fact is, and the Rosenbergs who introduced me to this subject area were trying to argue that there was a lot of vertical transmission, or quasi-vertical transmission, you could say, such that the microbes were deposited in the immediate vicinity where the host's offspring were, such that they were in a bird's nest, and so the nestlings pick up the microbes from the bird's nest. And similarly, microbes that are picked up in the birth canal in mammals. But I don't think that's the generic condition. And maybe that's my bias in focusing on marine organisms, where it does make sense to speak of a larval pool and a microbial source pool out in the water. So therefore, because I've got these pools, I'm assuming 100% horizontal transmission. Now, you could take them both. I mean, if there were any need to do it, you could then make a model that combined both and had a different fraction of vertical versus horizontal. But I just personally don't think that's worth the effort to do, because there's so many big questions out there, and what I'm working on at the moment is phage bacteria coevolution, because I'm very interested in whether something could be done to prevent the evolution of resistance to phage by bacteria. And if we understand phage bacteria coevolution, then we also would know how to intervene and stop it from happening, I hope. And so that's a long answer to your question, which is I just don't think that that's an important enough issue yet to delve into further, but it could be done.
There's a question over here. Okay, okay.
Hey, Joan, thanks for helping us. I was wondering, where are you, or in your collaborations with applying some empirical data on your models?
Nowhere. Because from where I'm coming from, the problem is to figure out the logic of this whole holobiont idea, and obviously it's a very stylized and simplified kind of model, and they are testable. There's no doubt about that. If you wanted to do that sort of thing, if we go back over here. Yeah, like let's take this. The condition for the coexistence of a host and a microbe. All right, suppose you had an experimental system where you had a host and one microbe. Then you could experimentally vary, in fact, you could vary D over here experimentally in a system. And so if D is high enough to begin with, that this condition is satisfied, then lower D, for example, by making the water more viscous, so that the microbes can't reach the host they're trying to colonize. So if you make this more viscous, which would lower D, then you'd flip, if it got low enough, you'd flip the inequality sign here, and if you got it low enough, therefore, at that point, the microbe could no longer coexist. So it would be an experimental test in which you could do that, and that would confirm the prediction of the model, if you found that out. So throughout here, you can always devise experiments which test these conditions for increased when rare or conditions for coexistence and so forth, without actually plugging in numbers for everything, because that would then be really ridiculous.
I think there's time for one quick question. So there's one over here. You can.
Hey, thank you. So back, maybe following this question, the model doesn't assume any selection on the microbes themselves by the host, just random invasion. And you just gave an example. For example, in the bobtail squid, we can see that the microbe is actually being, in practice, selected by the host, and you have only one microbe in this context. And maybe This way, this model could actually be tested, and also you can actually measure the rate of invasion on a single microbe and then extrapolate.
Yeah, so in this model here, this is just a straight population dynamic model, so there's no selection of any kind going on here. But nor is there selection by the host here. Here there's random colonization. But the whole point of this model, this is an alternative story. So I see there basically being two alternative explanations for the formation of this host microbiome integration. One explanation is selection on the hologenome, and I think that has the problem I mentioned, that you can't get much progress with directional selection. The other alternative explanation is host selection. And so in this one, there is selection by the host of the microbe that it will accept. And it's an interesting problem because neither party kind of knows what the other's doing, but there's a feedback that goes on. So the host right here simply reacts to the amount of photosynthate being given to it by the microbe. But by reacting to it, it thereby changes the colonization rate for the microbe, which in turn affects the ability of the microbe to colonize the host. And so that's the way the selection works. But one does have to be careful in this to make sure you're paying attention to who's controlling what, and then how that feeds back to the other. But thanks for the question.
Thank you. Thanks for a great talk.
Right, thank you.